Hello, thank you for coming. This is the Containerd Deep Dive session in which Derek McGowan and myself will try to elucidate how Containerd works a little bit. We'd like to do it in a semi-relaxed kind of mode. We know it's late in the conference and we're sure that you guys may have lots of questions. So we're certainly here to answer any questions. Derek will go through all the decks and give you a nice demo. Derek is a maintainer from Docker. He's been, keep closer. Is that louder? Is that better? Well, I'm sure the translators can probably hear me better too since they're in the room, right? So, to repeat just a bit, introducing Derek McGowan of Docker. He is a maintainer on Containerd. He works on all elements of it, but focuses on a lot of the file system components. He's worked on Docker distribution, the Docker registry. He's been around for a long time, and he's got a lot to share. Okay, so I'd like to turn it over to Derek.
All right, can you guys hear me okay? Good, translators? Okay, perfect. So I'm gonna kind of start off with where we left off in the intro. I mean, this was the architecture diagram that we were going through. So before we kind of had talked about some of the different users of Containerd, so like the kubelet, the different platforms, Prometheus. In this talk, we're going to focus more on the components inside. So the different services that we have available, as well as the plugin model that we're using in Containerd. So to start off, Containerd is essentially the client-server model. We have a smart client. The client implements all the high-level interfaces. So when you do, for example, a poll operation, the poll operation is actually implemented inside the client. Any sort of new functionality that users are asking for, most of those functionalities can actually be implemented in the client rather than on the Containerd server. The interfaces on the client, they may change somewhat rarely, but what we really focus on for stability with Containerd is our gRPC interface. So the gRPC interface gives you access to all the low-level components, all our low-level interfaces, and we consider it to be stable. Any 1.x Containerd client should be able to use any server. So sitting underneath, inside the server, we have our service layer. So Containerd service interfaces, these are what provide interfaces such as to the content store, to our snapshotters. So we actually have a service layer that can be used directly by plugins. It can be used by the gRPC service. It provides access to each of the components. And then we have a metadata store that sits right underneath it. So our metadata store is what will actually provide all the namespacing inside of Containerd. It's what adds all of the labels. And it is actually sitting on top of the snapshotter and content store, which actually store data on disk, so that you could have data that's on disk for one user and another user potentially using the same data or different data on disk, but all of that's going to be managed by the metadata store. So think of the metadata store as it's just a Bolt database in Containerd. It is top level key is the actual namespace. It was designed this way in order to support multiple clients. So if you're the CRI plugin, you're using a namespace called kds.io. If you're Docker, you're using a namespace called Moby. When you're using CTR, the namespace is just called default, but you can set your namespace to anything. And under that namespace, you have your images, you have your containers, and each of those are only for that given namespace. So the images that you pull, such as through CRI, you won't necessarily see those with Docker or if you go through CTR, unless you actually specify those specific namespaces. And it also allows us to have our labeling system namespaced.
Just that we also store our pod configuration and container configuration in the metadata.
In labels? Yeah, so the labeling system is just it's fairly robust. It's just key value stores. Every object in containerd can have a label. And looking at kind of how that data is structured, so we have data types for images, we have data types for containers, content, which think of content as just a blob of data referenced by a hash. So if you're familiar with the registry API at all, there's like a blobs endpoint, which just is referenced by hash. OCI images, descriptors, they always point to a specific hash. So the content store is just what actually stores those blobs of data. So in containerd, we decided we need a way to track all of this data, which could potentially get kind of large. A problem that people often have with Docker is after they've been using Docker for a while, their disk starts to fill up. And we've added some stuff within Docker, like pruning, that can actually help reduce some of that usage. But in the end, it's kind of harder, at least in the data model that Docker has, to clean up data. So for containerd, we decided to build that in from the beginning by having actually references between the data and having top-level references that users will be more familiar with, such as images and containers. So when you go to pull an image, it's going to pull down all the content, and then it's going to create an image that's going to point at that content. So in this chart, I tried to demonstrate what the containerd metadata store might look like if you had two images and you had a running container. So the Redis container will be based off the Redis image that was pulled from the registry. And all of these arrows in between, in containerd, these are actually just labels. But to the garbage collector, they look like references so that we know what can actually be kept and what can be removed. So if we were to come in and now say delete the Redis container, or delete the Redis image, even with the Redis container running, the immediate result would just be this. The image is gone. There's no longer a link between that image and the content that's being referenced by that image. The garbage collector is going to come along. It's going to see that there's content here that is no longer referenced by a root. And it's going to go ahead and delete that content. And as you can see, as soon as that content gets deleted, the links go away. What I said before, how each of the pieces of data in containerd can have labels, and those links are just part of those labels. So once the content is gone, so are all the links. So the end result is just going to look like this. We still have a Redis container running. The Redis image is completely gone. Notice here in the snapshots, it's still going to have that Redis unpacked layer, but there's no more image associated with it. So if now we were to come in and delete that container, normally when we delete a container, we also delete the root snapshot. The result's going to be the same, where this link is going to disappear. The garbage collector is going to come along, and it's actually going to delete that Redis layer as it's no longer referenced. And in the end, you're just going to end up with, I think, what you'd expect, which is we still have that Alpine image, the content, and the unpacked layer on disk. So let me switch over to talk about plugins for the snapshotter. If anyone has any questions, as Mike was saying, we can answer some of them along the way. It's kind of a big room, but if you have questions about some of the data model, go ahead and ask them, so there's not too many at the end. Okay, so for what a snapshotter looks like, the snapshotter is a fairly simple interface. If you're familiar with kind of the graph drivers that we have in Docker, there's a lot more operations you'd expect. Whereas for the snapshotter, there's no data operations, there's no mounting operations. We have immutability for snapshots, as in once you create a new snapshot and you commit it, that snapshot is immutable. There's no way through the API to mutate that snapshot anymore. Snapshots themselves can be labeled. As you saw in the previous diagram, some of those links, although the garbage collector doesn't need to use labels to create those links, since snapshots actually have a natural hierarchy. When you prepare a snapshot, you always give it the parent of which you're creating a snapshot from. So we also have the ability to kind of enumerate all the snapshots that you have on disk. So this is implemented through the walk functionality. So you can use the walk to see all the snapshots that you have, and CTR and tooling can make use of that. So in 1.2, we added a feature called a Proxy Snapshotter. So today we have three snapshotters that are built in, maybe three or four snapshotters built in. The main ones being OverlayFS, and then the most popular one, and the native driver, which is just a flat, which is every layer is just the full flat structure, kind of like the naive driver in Docker. So what a proxy snapshotter allows is you can actually use, in a configuration, you can configure a Unix socket to actually represent a snapshotter, and in that Unix socket serve a gRPC API of our snapshotter interface. So if you have this implemented, we have a gRPC interface that mirrors this and can actually be made available through gRPC. So to configure it today, you would update the etc containerd config.toml. There's a line in there called proxy plugins. It's type snapshot, and you just give it a Unix socket. So this is an example of how you would create one. So the second line in the main function, custom snapshotter, all that is an implementation of the previous interface that I showed. Register that with a gRPC service, start listening, and then containerd can make use of it. Now, one of the reasons why this is somewhat practical with snapshots and the way we designed it is the saying, since there is no mounting and there is no data operations, the API is pretty light. What actually gets requested of the snapshotter and what gets returned by the snapshotter is mostly metadata in nature. There's not a lot of transactional operations that need to happen between different runs of the snapshotter, so it can act fairly stateless. So we also added in 1.2, well, we didn't add, but we stabilized this API. So this is our shim API. Essentially what it allows is when you go to run a container, you can specify what your runtime is. In 1.2, we added a feature where, in addition to just specifying a runtime by name, that name can actually represent a binary. And that binary, as long as it serves up, when it runs, it can bind to a port and serve up this interface and act as the shim for your container that's running. So today you have to have, there's at most one shim per container, but now we have the ability to actually share the shims between multiple containers. So this is really practical for use cases such as Kata containers, where it's more desirable to have a single shim process that maps to a VM rather than mapping to the containers that get started through the Containerd API. So the main feature here, stabilization, but we also added a stats API here, whereas previously in Containerd 1.0 and 1.1, to get stats, you would have to actually talk to C groups on the host, which, as you can imagine, is problematic when you're running inside of a VM. You can't make use of those stats. So this allows any runtime to fully implement this interface and be much more useful to a broader range of runtimes. So those are the two of the main extension points inside the daemon. The other way to kind of extend Containerd today is in the client. So the client extensibility is mostly through our Go interfaces. So we chose to take an approach in our Go client where pretty much anything can be swapped out. So I gave an example of when you actually instantiate a Containerd client, we have this service object, which is responsible for actually connecting to these services that would be served by the gRPC API. And when you instantiate that service, you can overwrite any of the individual services with any implementation. So the arguments to all of these are mostly just the interfaces that Containerd itself has defined and uses all over the place, such as with snapshotters. This snapshotter interface is that same interface I showed before. You could actually add your own custom snapshotters directly on the client if you wanted, which would completely bypass the going to the daemon. This is used by the CRI plugin as well. So the CRI plugin, even though it's running inside the daemon, it actually uses the Containerd client, and it just instantiates all of these services with a local service. So it can be run both externally or internally without having any changes in the way it's designed. I also wanted to highlight, it's not necessarily obvious at first what a resolver means, but the with resolver is an option that you can give on any push and pull operation. Think of the resolver as a way to take a name and resolve it to a method for getting bytes or getting the blobs for that image. So in a pull flow, that would look like a process of resolving a name to a manifest and then just having a way to pull down the blobs for that manifest. So it's somewhat OCI specific in that it assumes that you have OCI manifests and tar blobs. But using this functionality, you could actually completely overwrite how you do distribution in Containerd. You can have it something that's completely customized if you don't want to use the defined Docker-based implementation that's now the OCI distribution spec. So a pull flow ends up looking like this in Containerd. This is completely orchestrated by the client. When a pull operation runs, that can be broken down into a fetch operation. The fetch gets all the content from the remote. It puts it inside the content store. Once all that content is fetched, the pull will create an image that points to the manifest. After that image is created, that's when we actually do the unpack, which will read the content that has been pulled and verified inside of the Containerd content store, and it will unpack it into a snapshotter. So the end result here is that you have an image that both has the content and your unpacked snapshot on disk. So the push flow is very simplified as well in Containerd. Since we have the content, Containerd defines no method of creation of that content. We defer that to tools like buildkit. So from Containerd's perspective, it has images and has content. And when you go to do a push operation, it just takes that content and it pushes it directly to the remote. In a Docker flow, there would be an extra step here that would be reading from a graph driver in order to recreate the content, recreate all the manifests. None of that is done in this flow here. So then the flow that we have today for actually running a container. So once we have these images and snapshots on disk, the first step is always we're going to initialize the container by reading that image, or looking at the OCI image specification, creating the snapshotter that's going to be used. So it can either create a new snapshot or it can use a snapshot or any route on disk that you give it. It's going to set up the container. So it actually creates a container object, which is going to have a reference to now an OCI configuration, as well as a snapshotter. And then once that container is created, it's going to actually start the task. And when that task starts, it's going to mount that snapshot and then actually call out to run C to start the container. Remember earlier when I was talking about snapshotter not having the responsibility to mounts, we move that responsibility to the running container step. So by having the running containers actually deal with the mounts, we no longer have to worry about inside the snapshotter various issues around mount namespacing and cleaning up some of those mounts and how many times those snapshots have actually been mounted. And Mike, you wanted to talk about?
Anybody have any more questions or any questions at all? Everybody tired after lunch or? Yeah?
Thanks, Mike. Hi, Derek. You have done a great job. I have a little confusion about the GC connect, 就是garbage connector. Yeah. If we delete the image, then the word image information has to be deleted. Even though the container is running. So I have a question is that if the upper system want to know the container's image information, how do we do that? Oh, thanks.
Yes, so in that case, it's really the responsibility of the client to determine whether or not it's okay to go and delete that image. So in the Kubernetes case, it would be the CRI plugin that would first check to see whether or not this image is used. Right. If the client can implement this in different ways, it could also set a label on the container that says what the image name is. But at least from the data model that we have in here, we're not opinionated about whether or not that container should be linked to that name after it is created. At least from here, we don't have a bunch of checks that would go in and try to kind of define these policies. So those policies are up to CRI plugin or Pouch to do.
So that was a very good question. Taking that along, basically what we do is when we receive a request to create a pod or a container, okay, then we store it using their metadata feature, all right? And then when we need to find it again for any purpose, for example, we want to do an update of the container image, then what we would do is go look at our cache copy in the metadata. We don't go looking at the original image, okay? But when we decide, okay, yeah, he's got a mode that says, check for updated images. Then what we'll do is we'll go back to container D and we'll see if we can get, an updated image. And then he'll go copy it. Right. So he sort of forgets that he deleted it, or he doesn't really care because we're asking for the latest, right? It might be colon latest. And then we get the new image and we, refresh the container. And then we tell Kubernetes, yep, we updated it for you, right? And then we update the metadata again for that container. Okay? Good question. Any others? Good.
My question is about something about multi-tenancy. Because when we want to run the pod, the image is pre-pulled to this to this node, right? Mm-hmm. And if tenant A had already pulled an image to this node, but tenant B supposed to not have access to this image, but he can guess and try. Maybe he successfully run other tenant's image because the image already on the node, and he just gave the pull process. Is there any kind of this roadmap to prohibit this kind of situation happen?
So there's two features that we have in Containerd to both support that and disallow it. So the default behavior is that when you have content that's pulled between two namespaces, when it goes to create the content in the second namespace, it sees that content is there. It'll actually be able to copy that. But we do have a feature in Containerd where you can disallow that. So it's like a strict mode where every single namespace is responsible for repulling that content, verifying it, and after it has verified it, it goes to commit that content. On the back end, it will share the content, but it first has to go through the verification step before it will add it into the new namespace. So that's similar to how the registry works today, whereas the registry, you can't just tell it you're creating content. Do you already have it? You actually have to prove that you have it. So we both have a mode where you have to prove it, but by default we don't have that since we haven't really defined how the security model on top of Containerd should work. It's really up to the clients to define. But yeah, that is something that we thought about and made sure that, at least from Containerd's perspective, we have that ability to support that.
Phil, did you want to talk about multi-tenancy at all, or no?
All right. Do you want to finish up these couple slides so I can get to the demo?
Yeah. Okay, so we're going to show an example to demonstrate how the Cry plugin works for the case when kubelet is creating a single container pod. Right? So you're going to have one pod and one container. If you went to the intro section, you probably understand that we do some namespace isolation around the pod. Specifically, there's a pod namespace for networking, there's user namespaces, things like that. We also have C groups that get attached, permissions, and they're all shared across the entire pod. All right. This represents all of the resources that you're going to use for your pod, and it represents the container that you're going to generate. You'll note here that we're using CNI for all networking. Okay. On the far left, it says daemon. Containerd is a process that runs. You can launch it with systemd or whatnot if you're on the right operating system, and it just serves up via gRPC the requests that come from Kubernetes, okay, to our container runtime. Thanks. Okay. So this is a quick flow. We're just going to create a pod. You'll notice it's very similar to creating a container because the pod is actually in our implementation actually includes creating a container called the pause container. We pull that image down. It's really small. We run it. We get it going, and we attach a network namespace to it. I'm going to go quick because he's got a good demo he wants to show you.
Well, a good one.
Okay. Here what we're showing is actually now running the container in the pod. Kubelet requests to launch the container. We go get the image, create a snapshot using the tools you talked about before. We set up our container, we store our metadata, that sort of thing, and then we start a task, and we have a running container.
All right, let's switch over real quick.
I know, it was quick. You can also ask questions after the meeting.
Well, you can continue talking about while this sets up.
You're setting up. Okay. Anybody have any questions about how Kubernetes works or with connecting to CRI if you didn't come to the intro section? Yes. Go ahead. Well, yeah, so the question was cryo versus container D. This is the container D pitch. Cryo is an interesting product. It can do pretty much the same things. It does work differently. We have different code sets. Okay, we had different goals in mind when we were developing it. Container D was built specifically to be a flexible, modifiable, configurable infrastructure specifically for programs like Kubernetes, like Docker, okay, like Pouch, who's using it.
All right, we can discuss that afterwards. I think that's a long topic.
That's no.
So yeah, I just wanted to quickly show kind of an example proxy plugin. So this is similar to what I showed earlier, but I kind of wanted to show it working. So if we have a simple app here, I'm just going to run a proxy plugin which uses the native snapshotter. So it's basically going to take the native snapshotter, which obviously implements the snapshotter interface. It's going to register it as a gRPC plugin. So there's a contrib that we have here, which you can import, and it will actually convert the snapshotter API to a gRPC service, and then register that service, listen, and then you're good to go. Let me show the configuration that I was talking about on container D. So this is just basically a default configuration. You can see I have a proxy plugin section. I call this test SS for test snapshot. The address is in this directory here. So let me go ahead and run that. Perfect. All right, so I'm going to pull down an image. So now when this image gets pulled down, you'll see we have defined a couple environment variables up here. The first one defines a namespace, just a demo namespace, the snapshotter test SS, and then it's just CTR images pull. It's pulling from a local registry, so it's going to be really, really fast. So the last step at the bottom is always unpack. So the unpack actually was able to make use of that proxy plugin, which I had here. So there's this root directory here. So this is just the standard native snapshotter. There's a metadata DB. There's a snapshots directory. Underneath that snapshots directory, you'll see actually all the individual snapshots. So 6 was probably going to be the latest one. It's all going to be flat Let's see, what else do I want to show real quick since we're at the end here. Let me go ahead and show how you can view these with CTR. So we have a tree command under CTR that's pretty useful. It actually shows the relationships between the different snapshotters. So this one here is actually going to be the leaf. So this would be the parent-most layer. Same ID. Yeah. So I can actually take that layer. I can create a new snapshot. So this is creating a new snapshot called upper one, CTR snapshots prepare, using this. So this is the same operation you'd expect to be done when you launch a container. It's actually going to prepare a brand new snapshot for you. We also have a neat command. Remember I said snapshots don't mount, but CTR will output a mount for you. So this is a mount command you could just give to Linux, and it will run it and mount it wherever you want. But as you can see, since it's the native snapshotter, a mount is just a bind, and it's binding to the directory 7, which has the full root file system for that image. So let me just go ahead and clean that up and show you what happens when we remove this. So these are the garbage collection logs. Not super interesting. You can see that a garbage collection happened. Garbage collection in Containerd runs pretty fast. In this case, the content garbage collection was 6 milliseconds. This is actually all the content that got removed from disk. So this scheduling of the content cleanup, this is actually what removes data from disk. Since it's pretty small, didn't take that long, only 6 milliseconds. The 4.9 milliseconds is the amount of time that we actually had the metadata store locked. So we made sure to put that as a statistics. All right, yeah, that's all I'm going to show about that, but we're going to be around afterwards, so come and ask more questions about Containerd. All right, thank you, everybody.